Okay, so binomial distribution. We'll just be talking about two distributions. Well, probably just one for today. So one special distribution, and we've touched on this distribution for a while now. My computer really doesn't like probability and just has to think really hard right now about whether it wants to cooperate or not. It seems it's coming down on the not. Okay, thank you. Okay, so we're going to look at a special distribution. And that special distribution is actually made up of really small little experiments. So the little experiment that I'm talking about is called a Bernoulli experiment. And that is a random experiment that only has two outcomes, success and failure. And we've seen a couple of these kind of experiments for the last couple of hours already. So you can think of a coin flip, so head, tail, rolling a 6 or not, winning a major tournament or not. So a lot of experiments are made up of these kind of small Bernoulli experiments. And the probability, so we will assume that success is mapped to 1, failure is mapped to 0. And just for convenience, we will define the random variable to be not really in R, but and by R I mean the real values, not the software. So the probability of success is defined as little p. So little p is somewhere between 0 and 1. And correspondingly, because we only have two outcomes, the probability of failure is therefore defined as 1 minus p. So then we've got our random variable. X has two different values. It has a 1 for success and 0 for a failure, which means that we can write out the probability mass function for failure as 1 minus p and success for p. And we can also write out the expected values. So as 0 times 1 minus p plus 1 times p, that's just p. And for the variance, we look at the difference between each outcome and the expected value. We square that, multiply by 1 minus by the probability for this outcome, and then repeat the same thing for the other outcome. And that gives us a variance of p times 1 minus p. So the variance is particularly small when we're at either end of our probability spectrum. So if p is really small, this is fairly small. If 1 minus p is fairly small, this is small. And the variance is the biggest if both p and 1 minus p are in the middle. So the variance is maximized at a fourth if we have a 50-50 chance for success and failure. So let's have a look at an example. And I would highly suggest to you that you use discrete RV in your approach to this. So we have a random experiment. It's a Bernoulli experiment. We hit a target with chance 1/10, which means that, the yellow bullseye. So we assume that our we've got a novice shooter, a novice archer. And she hits the target. Let's assume she hits the target. She's not that terrible. And the chances of hitting the yellow bullseye is 1 in 10. And assume that she's trying 3 times and she doesn't learn over those 3 attempts. What is the probability mass function in this situation? What's the expected value? What's the variance? So we are talking about Bernoulli experiments, and now we're piecing together Bernoulli experiments. If you think back, we've already done that a couple times. So try to use R to solve this question. I'll give you 3 minutes. 5 minutes. I'll give you 5 minutes. Then we have time to talk through this and generalize it a little bit. All right. How did that go? I hope that this example looks really familiar, that it looks almost similar, very similar to what the Grand Slam problem looked like. So let's have a look at the code. We'll use very similar code. So let's assume that we've got a shot, and shot again here means we hit the yellow. We hit the yellow of the target. So 1 means we hit it, 0 means we don't hit it. We hit the yellow bullseye with 1/10 probability and 9/10 to not in 9/10. So then we do 3 shots, and we only want to count how often we hit that yellow bullseye. So we take the sum of 3 shots, n equals 3, sum of those IID shots. And that gives us a random variable with those 4 outcomes, 0, 1, 2, 3. We hit the yellow bullseye 3 out of 3 attempts with probability 1/10 times 1/10 times 1/10. So 1 in 1,000. Most likely we don't hit the yellow bullseye at all. That's 72.9%. And then the rest is somewhere in the middle. So we can take the expected value of this random variable. And in the code, it's just a call of, we get 0.3. What's happening with the expected value outside is we take the probability, the product of 0 and its probability, 1 and its probability, 2 and its probability, 3 of this probability, and we sum over those. The result is 0.3. And for the variance, we get a 0.27. So 0.3 means that most likely in 3 shots, we're not hitting anywhere close to the yellow bullseye. Well, maybe close, but not the yellow bullseye. And variance of 0.27. What standard deviation does that correspond to? So square root of 0.27 is about 0.5. So standard deviation 0.5, 0.3 plus minus 2 times the standard deviation. So that would be negative something, we don't care. So between 0 and 1.3, that's where 75% of our probability mass falls into. So between 0 and 1, and we see, yes, Chebyshev is true. There's quite a bit more than 75%. So that's why we're also looking at the variance. Okay, so this is already, okay, so we can do the same thing by hand. It looks very impressive, but it's the exact same thing that we did before. And this is an example of the special distribution that I was talking about. So this is an example of the binomial distribution. So binomial distribution is defined as sequential Bernoulli experiments. So we take n sequential Bernoulli experiments. Each one of these experiments has a success of p, and we assume that the trials are independent from each other. In a binomial distribution, we're then interested in the number of successes, x. So we define x as the number of successes in those n trials, which means that we have a sample space for this random variable from 0 to n. And we can set up the probability mass function for the number of successes as this probability that x is equal to k, where k is any one value between 0 and n. Hide a bimodal distribution, or is it just a unimodal normal distribution? There's a paper behind all of this, but I thought just this visual was very impressive. So normal distribution. The normal distribution is this archetypical bell-shaped density curve. So usually we think of the normal distribution just as this curve, this very nice symmetric curve with a single mode, an infinite sampling space. So we've got an infinite, we can potentially get infinite every single value in R, but we have a space around which the values are usually centered. So we've got two parameters. We've got a parameter mu and a parameter sigma. Mu is the location parameter. So a different value of mu is going to shift our distribution along the x-axis. So here we've got this green curve, and you can see this is the only one where mu is different from 0. Mu is here set to -2. So it's shifted to the left, and the peak is now centered above the 2. So mu is also giving us the location of the peak in this density function. So sigma is the so-called scale parameter, and that determines how flat the curve is or how centered the curve is. So a large value of sigma is going to give us a very wide curve. So sigma is 5 here. A small value of sigma, 0.2, gives us the sharpest curve, so with the steepest slope and the most centered values. So this general form of this curve, of this density, is given by essentially this exponential expression. So we've got a centering value of 1 over square root of 2 pi sigma squared. When you have a look at this, this is just a constant. So this is just a constant to make sure that when we integrate over this function f, the result's going to be 1. And then we've got an expression of e to the negative x minus mu over 2 sigma squared. So we've got an expression that is that is the highest in when x is equal to mu, and then we fall off symmetrically to both sides. There's a square missing. I'll fix that. I'm sorry about that. So we've got expected value of mu and variance of sigma square. So you can see where those parameters are coming in terms of mu and sigma. And we get a corresponding distribution function. We'll denote that as n for normal with parameters mu and sigma square. And the distribution function is again giving us the probability that x is at most t. So that's this integral over the density function from negative infinity to t. Now, the problem is that this integral doesn't have a closed form, so it's not a nice integral. So we either need to use lookup tables or we use some software. So you know where my approach is. I'll go for the software and look at how we can get those actual values for the probabilities out. So in the reason why we like the normal distribution is it has a very nice propagating property. So when we've got two random variables that are linearly distributed, that are normally distributed, normally distributed, any linear combination of these normal random variables is going to end up being normal again. So this z, which is a combination of x and b and y, is also a normal random variable. And we know what its parameters are if we know the parameters of x and y, because we know what to do with linear combinations of expected values and variances. So the expected value is again just a linear combination of the expected value of the individual random variables. And the variance is this essentially squared expression of individual parameters and their mixed form, so the covariance of x and y. What this expression also allows us is, it allows us to get every normally distributed random variable into a standardized form. So if we've got a random variable x that's normal with parameters mu and sigma square, if we subtract mu from this x and we divide by sigma, we end up with a random variable that has what we call a standard normal distribution. So it has a mean of 0 and a scale of a variance of sigma square of 1. So the only distribution that we really need to talk about when we're talking about a normal distribution is this standard normal distribution, because we can get every random variable into a normal distribution and then we can get results back. We can back transform the results into the space, into the units of the original variable x. So that makes working with normal distributions very, very convenient. The calculus is very nice. So in R, we've got a name of the normal distribution as norm. The random variable, or creating random variables, is then done with R norm. N gives us n many, and by default we're sampling from a standard normal distribution, but we can set the parameters. Just note how this random generator is parameterized. So this mean is the location parameter, so that is mu. SD stands for the standard deviation, and that means sigma, not sigma square. So it's not mean and variance, it's mean and scale. And again, D stands for density, P is the distribution, and Q is the quantile. So that's the same for all distributions, all distribution families in R. So let's try this out. Hearing again? Okay, not sure what happened here, but I'll just show you the slides without going into the full mode. So let's have a look at some SAT scores. So results from the 2018 SAT scores had a mean of 1,086.68 and a standard deviation of 204 points. So let's assume that the distribution of the SAT scores is a normal distribution with those mean and standard deviations. And then we can come up with probabilities that a student who took the exam in 2018 had a score, an SAT score between 800 and 1200. And then we can also have a look at what the probability was to score higher than 1400. So instead of working with this normal distribution, we can standardize the SAT scores by subtracting 1068 and dividing by 204. Then we'll get a standard deviation, a standard normal distribution out of that. So let's try to do that. So we have a look at the Z values corresponding to 800, 1200, and 1400.
Oh,
and we can, yes, sure.
Yeah, so the initial, if you go back one slide, so the initial distribution, do we know that it was a normal distribution, or if you just take out the mean and the standard deviation from any distribution, it becomes a standard normal distribution?
That's a good question. So we would need to, so we can get the mean and the standard deviation for pretty much any set of numbers. But what we really need to also do is we need to have a look at the distribution of these numbers in, say, a histogram or a dot chart to see whether we actually see this prototypical bell-shaped curve. There's also, so that would be a visual inspection. So we're looking for a unimodal distribution that's more or less symmetric. Another way to check for normality would be a test. So there's a lot of different tests that test for normality. So there's Shapiro-Wilks. There's a lot of other tests. We can also have a look at so-called quantile plots. So we can plot the quantiles of a normal distribution and plot the sorted values of the vector in a scatter plot, and we hope that we see a straight line. So there's different ways of checking whether those normality assumptions actually hold. For right now, let's assume that we did that and that distribution of the SAT scores actually turned out to be normal. But it's a really good question. We shouldn't take it for granted that everything is distributed normally. But a lot of things are, and we'll see why in a little bit. And that's really what makes the normal distribution so powerful. So for now, please accept that the SAT scores can be approximated by a normal distribution. We'll just assume that.
Thank you.
But good question. Okay, so once we've got this normal distribution, we can standardize it by subtracting the mean and dividing by the standard deviation. And we get these critical, the so-called Z values out. So now we can plug those z values into a standard normal distribution and get our different distributions out. So the probability that somebody in 2018 had a SAT score between 800 and 1200 is equal to this value minus this value, which is which turns out to about 65%. So that's sort of in the middle. So for somebody having a score of above 1400, that's the complement of being of less than or equal. And I said for continuous distributions, we don't have to be that fussy about the equal symbol, but proper math would be to have an equal, less than or equal sign here. So we put in the z value for 1400, and we come up with a probability of 5.2%. So having a score of above 1400 already puts somebody in the top 5% nationwide in 2018. All right, so easiest way to work with normally distributed random variables is to standardize them by subtracting mean and dividing by the deviation. And we can do that because of the linear propagation property of a normal distribution. So I'll hand over to you. So I didn't get rid of all your turns. I just heavily downsized those your turns. So I'll give you 3 minutes and you can see whether you can work this out. You can use R if you want to. What we're trying to find is values for t such that C, this area under the curve, is 0.9, so 90%, 95%, or 99%. So what are the values for t in those cases? Those values are called the critical values, and we'll come back to those values of t again. Did you find values for t? Do you know those values by heart? Okay, so these are the kind of values that you will, after a while, know by heart. So how do we get to those values? So we want to find t's such that the probability that x is between plus minus t is exactly c. So we've got values for c of 90, 95, 99. We'll get to that, but let's just solve it in general. So the probability that x is in this interval, that's in terms of the distribution functions, that's the probability, that's the distribution function in t minus the distribution function in minus t. Then we know that the distribution is symmetric around 0. So we can rewrite the distribution of a negative number as the complement, so 1 minus the distribution in t, which gives us 2 times the normal distribution minus 1. So C is the probability that we want to find, which means that if we solve now for t, we get some value in, we get some expression in C. So the t is equal to the quantile. So the negative one is refers to the inverse of the distribution here, not the inverse of x. That's a little bit, that looks a bit strange. And the quantile that we're looking for is c plus 1 divided by 2. So we're looking for a quantile. So if C is 90, we're looking for the 95 quantile, a 0.95 quantile of the standard normal, and that gives us a T of 1.645. For C of 95%, we end up with a value of 1.96. So hopefully that one looks familiar to a lot of you. And then if we're looking at the 99, if we want to have 99% of the probability between values negative T and T, we need to go up to a value of T of 2.576. So then 99% of the probabilities will be inside that interval. Okay, so we'll come back to those critical values. In particular, the 1.96 is important here. I'll refer back to that table when the time comes. So the question is still out, what makes the normal distribution so special? Let's have a look at a physics experiment for that. So you might have seen this Galton board. We've got a little container with balls, and the balls are released and go over a triangular grid of pegs. So at each peg, a ball can go to the left or the right. So it's not deterministic. It's a random experiment that's run with every turn of this Galton board. And you can see that the overall shape is very similar in each one of these instances, but the location of each individual ball is random. So what is going on there? You can see that we have a density, the normal density sketched out, and the balls fall pretty much in that density. But what's really going on here? So let's have a look at that. So we've got this, so here's a sketch. It's a sketch from Wikipedia. So here's a sketch, and you can see that a ball is released. At each one of these green pegs, it has to make a choice between left and right. And then at the bottom, it's going to end up in one of these bins. So we've got bins, let's call them from 0 to 7. And we just count the number of decisions to the right that the ball takes, from 0 to 7 in this case. So at each one of the locations, the ball makes a decision regarding left or right. So that's a Bernoulli experiment, left and right. And we've got a sequence of these Bernoulli experiments, which means that essentially we are dealing with Bernoulli experiments and then the sum of Bernoulli experiments, which means that what we're seeing down here is really not a normal distribution. It's really a binomial distribution with 7, in this case, 7 trials and a probability for success. So a probability to go right of 50%. But this looks like a normal bell curve. And the question is really why? So the thing is that this is not a coincidence. This is a direct conclusion of the central limit theorem. So what does the central limit theorem tell us? The central limit theorem is telling us that a sum of random variables might be normal. And the condition for this really hopefully startling result is that all of these random variables have the same distribution, so they're identically distributed, and they have to be independent. So one, having those random variables executed one after the other, we can't have any dependencies between those random variables. So if we have random variables x1 through xn, and they are all identically distributed, so they all have the same expected value, they all have the same variance, but we don't know their actual distribution. So they could be uniform, they could be binomial, they could be something that doesn't have a name. We just need to know that they are identically distributed, so they have the same distribution. Then the sum of them is approximately normal distributed, and the distribution parameters are given by as n times the expected value and n times the variance. So that means that if we have n binomially distributed, n Bernoulli distributed values, a binomial distribution can be really approximated by a normal distribution. So that's the reason behind the Galton board. SAT scores are the sum of small, SAT scores are the outcome of a test. So each test consists of a set of questions. We can maybe assume that the questions are of equal difficulty level. That's probably not quite true, but let's assume that. And those questions are answered sequentially if the student doesn't get flustered during the test, which is another big assumption. So let's say they're independent answers. The sum is the SAT score, and we can make the argument that because of the central limit theorem, we might say that the SAT scores are then approximately normally distributed. Okay, so sometimes the central limit theorem is not stated as a sum, but it's a theorem for the averages. So let's say that we've got n observations, and we'll assume that those observations are coming from n independent, identically distributed random variables. And we take the sample mean of those observations. So we just take the average, we take the sum of those random variables, we divide by n. That's called the sample mean, and we'll denote the sample mean as x with the bar on top. Then this sample mean has an approximately normally distributed with parameters mu, so the same expected value as each one of those observations, and a variance of sigma squared divided by n, so a smaller variance than each one of those observations. And that's because the mean is somewhere central in the data, in those observations, and doesn't move nearly as much as individual observations do, as individual observations move, so it doesn't move by a factor of n as much as each individual observation. So here we're referring to this as the limiting distribution. So the distribution is only approximately normal as n goes to infinity, which obviously we're not going to ever see, but as n goes to infinity, that's when the distribution is equal to the normal distribution. So this is just another way of phrasing this approximately normally distributed random variable. Okay, so like I said before, there's a lot of different distributions that can be now approximated by a normal distribution. The binomial distribution can be defined as the sum of IID Bernoulli, which means that we can approximate any binomial distribution that has parameters n and p by a normal distribution with parameters n times p for the expected value and n times p times 1 minus p for the variance. Generally, we say that this normal approximation holds if the distribution is relatively symmetric and has relatively enough trials in it. So if n times p is greater than 5, and at the same time n times 1 minus p is greater than 5, we say that the distributional approximation by the normal holds. That's just a rule of thumb, but the values are quite close. So we can go through a situation where the distribution, where the approximation doesn't quite hold yet. So here we've got an example for 120 patients that are treated for high blood pressure, and the drug that they're taking has a side effect of indigestion for about 3% of the patients. So now we can check the probabilities. So this is a binomial. The number of patients that have indigestion is really a binomial distribution with 120 patients and a probability for well, indigestion. I don't want to call that success, but a probability for the side effect that's of interest to us of 3%. Then we can say that the probability, then we can express those that, that number of patients has a binomial distribution. Actually calculating the binomial distribution for 120 trials, the computer might be able to do it. We certainly don't want to set up the sample space by hand because we would need to write out sequences of length 120, and there's a lot of them. So another way to go about this is to use a normal approximation to the situation and assume that we are dealing with a normal distribution with parameters. What's mu? Mu is 120 times 3%, so not sure what that is. I need a calculator. 3.6. So n times p is a bit less than 5. So if we use a normal distribution assumption here, we can actually see small differences between the binomial distribution results and the normal distribution results. So I'll let you do that. For now, let's stop with the material for day 1 at this point, and I'll take any kind of questions that you might have.